Good morning, ladies and gentlemen. A lens is a transparent medium with an index of refraction larger than air's. Let it soak in. That makes sense.
Yeah, remember when we were playing with this stuff?
Yeah, because it bends light, right? Okay.
Yeah.
Lenses form images by refracting light. Look at that, guys.
His
Smile.
mouth is not that big.
No, it's not.
That's
okay.
a magnifying glass.
Okay, so convex lenses are converging rays, and light comes in parallel, goes to the lens, and focuses on a focal point, and we have an image.
And we saw that when we went outside and projected the sun onto the piece of wood.
Now how could you find the focal length? Well, we could measure the distance from here to here, right?
Well, we did that yesterday. We went out in the sun and we measured that.
We could measure.
We measured it. And then also we used the optical bench to find the location of the image for an object at infinity, and that was the focal length.
Yeah, okay. So we measure here, but then also we did the distance, the object distance of the image.
Yep.
Okay, yeah. Okay. It's all coming back to me. Okay, concave lenses equal diverging rays.
Yep.
All right, the light comes through, it's bent that way, no image forms, they're a little bit boring.
Now, Mr. Boykin's glasses are thick on the edges and thinner in the middle. They're diverging, and if you look at the side of my head, it makes it look like my...
Can you guys see it? Look straight through, straight Boykin. Straight right there. You see how it's a little in right there?
Looks like I have a dent in my head. I ain't got no dent in my head. What's happening is these lenses bend the light and make it look like I've got a dent in my head.
Real images formed by a convex lens can be projected on a screen.
Yep.
And that's what we saw yesterday.
Yep.
Yesterday was all with convex lenses.
Yeah.
The image can be located by using a ray model diagram.
Oh, we gonna go there?
Ray model diagrams. Okay. So a spherical convex lens has two focal points. Okay. So that means when I draw my principal axis, I draw my lens, I'm going to have two focal points that are going to be equal distance on each side.
That's right.
Right? Okay. Light coming in parallel to the principal axis is refracted through the focal point.
You know what? Let's
Should we start drawing?
Let's start drawing right now.
Okay, let me go ahead and just draw a principal axis in there. All right. Okay. You can do this, Val.
Start at one end, go to the other. Okay, make a mark at 50.
Thank you. Thank you.
That'll be where the location of the lens.
Okay, and I'm just gonna make a mark here at 16. Oops. And then here at, again, is it 36? No, 34.
Yeah, 50 minus, you want 16 centimeters. We'll find out why here in a minute, boys and girls. Okay, so you want to draw in the lens there in the middle with the protractor?
No freehanding. Okay, so this is my focal point, and then here is where my convex lens is.
And on a ray model diagram, you just represent that with a perpendicular line.
Yeah, you don't have to draw it any specific way.
Yeah.
Just like that. Okay.
So, light coming in parallel to the principal axis are refracted to the focal point. I think we should keep going on the slides. We can come back to this when we do the diagram.
We'll come back to it. And what do these words mean here? Light comes in here, and then that's that focal point that we just drew.
Yep.
Okay, so we'll do that in a little bit here. Light coming through the focal point is refracted parallel to the principal axis. So anything that comes to the focal point like this from the tip of here, and then is then refracted parallel to the principal axis that leaves parallel.
Yep.
Okay, and you can see that's where we get our image.
And there's many similarities to what we were doing with mirror diagrams, ray model diagrams for mirrors, because they behave similarly.
Yeah. All right, so let's do a practice problem. Okay, so draw a ray model diagram for a lens with a focal point of 4 centimeters. Okay, so take a look at this. So on your paper, you're going to want to draw a straight line here with our lens right here in the middle, and you're going to want to measure out from 0 to 4 centimeters here.
4 centimeters to the right.
And then the same thing over here. Does that look like it's in the middle?
4 centimeters to the left.
It doesn't look like it's in the middle. Now that I'm looking at this. So this is 50. Oh, you want to know
you
why?
got 26 over here on the right.
I was like, hold up. the importance of taking a step back and looking at your work.
That's right.
Okay. Okay, focal point right there.
Everybody makes mistakes. For example, I got out of bed this morning.
Yeah. So here we are. Okay, so now this is this represents 4 centimeters for me, 4 centimeters on that side. You guys should have the same thing. Do it. Okay. So draw a diagram, focal length of that. Find the distance of the image and the height of the image for these things. Okay. So I'm just gonna. What I like doing, Boykin.
Yeah.
I like doing this. I don't know if you like doing this, but this one doesn't.
We
matter.
don't need the center.
Yeah. So the distance of the object and the height of the object. Okay, so it's going to be 9
centimeters and 2 centimeters.
And 2 centimeters. And we're trying to find the distance of the image and the height of the image, yes?
Yeah.
Okay, so.
Let's put our object over on the left. Pick a point, boys and girls, 9 centimeters from the lens.
Okay, so
on the left, make a mark. So 9 times 4 is
36, right?
Yeah.
Okay. It's going to be right there.
And then we're going to make it.
I'm just going to draw my line here first, and then I'm going to shorten it based on how high it's supposed to be.
So should be 8 centimeters.
8 centimeters? I don't know if that's long enough.
I think it is. I think it's too long.
Okay. Let me get this guy here. There we go. It is too long. Right there. Let me make sure it's all. Okay. Boop, boop. All right.
Okay, so she's located the object
Okay.
at 9 centimeters, and it's 2 centimeters tall.
What is next? Do I have?
Well, let's go back to that slide.
Right, this one, right?
Light coming in parallel to the principal axis is refracted through the focal point. How can we make a line parallel to the principal axis into the lens?
You know, we got to measure over here, 8 centimeters. I'm gonna put it right
For you
there.
boys and girls, it's 2 centimeters.
2 centimeters for you. Sorry, don't. Yeah.
See, we got to make this on the board big enough so you can see it.
Yeah. Okay, so there's my first ray.
Okay,
And
it
then-
comes in parallel and then goes through the focal point on the other side.
Okay, so something like. Oh, I bent my thing a little bit here. All
There you
right. Oh, it's nice that I can just.
So this is the first ray that you're going to trace.
Mm-hmm.
And then the next slide.
Okay, so light coming through the focal point is refracted parallel to the principal axis. Okay, so that means I've got to come in through the focal point right here, just like this. Now this is very similar to before. The only difference is instead of going through the lens, we
bounced off the mirrors.
Yeah,
now
for both
this is
of
a
these.
lens where the light goes through the lens.
Okay.
Now the question is, how can we make a ray parallel to the principal axis?
Okay, so I'm gonna go ahead and measure this right here. Now notice I'm using different things to measure different things. I'm gonna call it
How many centimeters is it on the board?
6.5. Oh, 6.5 on the board. So 6.5.
6.5 divided by 4 is 1.625.
1.62. We'll call it 1.63.
Yeah.
What did I say it was, Boykin, on the board?
You said it was 6.5 centimeters.
Okay, so let me just go ahead and draw a. Oh wait, what's my next step here?
You need to measure the distance. You need to measure that 6.5
Yeah.
down.
So this is what I usually do. Is this how you do it? How do you do it, Boykin? I usually just go like
I
that.
would, on this one, yeah, I just make a dot like
Like
that.
that? Okay. All right, and then.
Got to connect those dots.
There we go. Like that, okay?
And then the object is located where the head of this, the head of the object is right there.
So it's gonna
So
be
you need
right-
to draw an arrow.
right in there.
Yeah.
So this is gonna be an arrow head, not a ray head. So I'm gonna call it right there. Right there.
Okay, so now we need to know the distance from the lens to the image.
Okay, so I measure 20 28.5.
28.5?
Yeah.
28.5 divided by, oh jeez, 28 point, good lord. 28.5 divided by 4 is 7.13
7.13. Okay.
centimeters.
Centimeter. Oh, I forgot my units for these. Okay, what are we talking about? Elephants? Okay. So, for ladies and gentlemen, what you guys should have got is, so we're 9 centimeters here, 2 centimeters here, and 7.13-ish centimeters here, and then 1.63 centimeters high.
Now, you at your table, you know, you're working on this, you will not get the same results because
these are my lines, right?
Yeah, where could you make mistakes?
Up.
And we could have made mistakes. You're making mistakes. We're making mistakes. That's just the way it is.
Yeah.
So, but this is the basic idea.
Yeah. So, you know, the process is what's important. And what I want you guys to do is the same exact thing, but now your distance of your object is going to be 8 centimeters. Height will stay 2, so change this to 8.
Yeah.
And then one more where you change that to 6.
So ray model diagrams. On your mark, get set, go.
Okay, 2
Pause
minutes.
this and come back when you're done.
You guys ready?
They're ready.
Okay. So you can check the accuracy of your diagram by drawing a third ray through the center of the lens. Okay. So.
The center of the lens would be right there on the principal axis.
Yeah. So right here. So from there to there, right, Boykin?
Yeah.
Okay. OMG, look at that. I'm close.
Yeah.
Okay, so it looks like the height, I should have had my height be a little bit bigger, and it looks like it's a little bit closer in than what I actually got.
Yeah.
Okay. But that's not bad.
Although, if you look at this, it looks like you're a little high.
Oh, yeah. So if it's a little bit down lower, so if it's down a little bit lower, you know, what does that do for me?
Yeah.
It puts a little bit more on track there.
So,
Okay.
every time you draw a line that's a possibility for error, and just be careful and take your time and do a good job.
Plus, how thick are these markers? You
I know.
Yeah,
I
so
know.
all the things, okay? So if the object is inside the focal point, so this was, what did we say? Was it was 4 was the focal point?
Yeah.
If it's inside the focal point, the upright virtual image is located on the same side as the object. So check this out, right? If it's behind the focal point,
Well, the object is right here.
yeah, and since it's in front, well, the rays never converge, right? They never
They
converge.
go
anywhere
through
over
and they
here.
diverge.
So yeah, so you have to trace your steps backward. You know, we're not going to practice
But
that.
look how much bigger it is. So this is the way a magnifying glass works. When you look at something through the magnifying glass, it makes something look larger, and it's a virtual image because you're inside. You're closer with this than the focal length.
Very cool. Okay, and that's all about being inside the focal length. Upright, virtual is on the same side of the object. Okay, if the object is at the focal point, all refracted rays are parallel, so no image is formed, right? And so they just go parallel to each other, and if you go backward, they're not going to diverge either.
Yeah, and that's the same kind of thing when we had the concave mirrors. You get to that point where there's no image. It's like scrambled eggs. You can't see anything.
Yeah, there's nothing there. Okay. The mirror equation is also the lens equation.
Wait, what?
I know. We talked about this.
Yeah,
yesterday, right?
I know.
I know. It's not that surprising, but that's a nice thing.
So we can use that. Oh, calculate the focal length.
Oh, sorry,
no, of each lens. So you have done.
You've done 3 of them now. We've only done 1.
Yeah.
Okay. Oh wait. Let me go to the next slide. Oh yeah. Yeah. Let's go ahead and do this one. Yeah.
Calculate the focal length of each lens. You know, this doesn't make sense
Oh,
right
wait.
now. Let's go on to the next one.
Okay. Calculate what the distance to your images should be.
Yeah, that's what we should do.
Should we do
right
that?
now.
Okay.
Yeah.
All right, so our equation is 1 over f equals 1 over the do plus 1 over the di.
And we want
And
to
we
find
want-
the distance to the image.
Okay, so 1 over f minus 1 di. Okay, so 1 over 4 centimeters minus 1 over 9 centimeters
Yeah.
equals, what do we get?
Better be something in the neighborhood of 7.
Minus 9 to the negative 1 equals, and I get 7.2.
7.2. So your diagram is remarkably accurate.
Woo-hoo! Dang, Miss Moore.
7.2 centimeters.
Sweet.
Yeah.
Nice. Okay.
I wonder if there are any other similarities with mirrors. What comes next?
Ah.
Heidi Hodo.
Heidi Hodo. All right, so magnification by lens is that right there.
So if we wanted to, well, does it ask us to find the magnification?
Calculate what the height of your image should be. Okay, let's do it.
So if you want to find the height of the image, how do you get rid of the ho?
How do you get rid of the ho?
You multiply it both sides, so it's ho-de-do.
Equals a ho.
D.
Do.
Ho-de-do.
With a negative there. Don't forget the negative, okay? And let's see. The height of our object is 2 centimeters. Times the negative height of the image, which I'm going to use the 7.2.
Yeah.
Because that's the,
That's what we calculated.
yeah. And then the distance of the object is 9 centimeters. This blue looks really nice. It's nice and crisp.
Yeah.
I love a good marker. Okay.
I know.
All right, so 2 times a negative 7.2, that's negative 14.4 divided by 9. And I get negative 1.6.
Look at that.
Wow.
Look at that. Now, what does a negative mean, Ms. Moore?
The negative just means that's inverted.
That's right.
Right. Which we see over here.
Yeah, we had 1.6 centimeters, 1. So that's a for drawing on the board. That's an excellent result. Boom!
Right. All right. So you guys do the exact same thing for not the focal length. Ignore that. Okay. Calculate the distance to your image for the other two.
Yeah. See how close you got.
And same with the height of your image. See how close you are.
So do that.
Okay. All right. For each of the following, locate the image, find the height of the image. So locate the image, find the height of the image. Is it real or virtual? Is it upright or inverted? These are all the things that you need to properly describe something.
Yep.
Right. Okay. So
let's just do this. Let's do the same with what we've got right here. Okay. Locate the image. That's the distance to the image.
yeah. Oh, right here.
Yeah. So that's going to be 7.2 cent. Well, let's use our calculated stuff here.
Wait.
In
What
red.
is it? What do you want me to do again?
Oh, go back to the previous slide.
Okay. Oh.
So-
Let's talk about this here.
Yeah, see, here's what we're going to ask you to do. Locate the image. That's the distance to the image.
Yeah, and that's gonna be this thing right here, right?
Yeah.
7.2.
Yeah.
Okay. 7.2.
Find the height of the image.
Okay.
That'll
That's
be
this.
right here. Is it real or virtual?
It's gonna be real.
It's real because it's on the opposite side from the object. It can be projected on a screen.
Yes.
Is it upright or inverted?
It's inverted.
Because it's negative.
Okay. Those are all the things.
So now, here is your assignment, boys and girls.
All right. So you've got a focal length of 4 centimeters, a height of 2 centimeters, and a distance of 2 centimeters. Okay. And
Let's do this one. Let's
have
just
two more.
run the, because I'm looking at this and I'm remembering a slide from a moment ago, and I'm
Yeah.
saying we should get some interesting results here.
so I'm just gonna do the math right first.
Yeah, you could. That's a beautiful thing, but you could erase all of it.
Yeah. I don't think we need this.
Yeah, we're not going to draw a diagram.
No diagram. Okay.
Yeah, leave it up
I'll
there.
do it.
That's a lot of work.
Okay. So what do we got here? So
We want to find the distance to the image
okay.
first.
So we want to find this right here.
Yeah.
So I should have kept that part up here. 1 minus the DL equals 1 over the DI. Okay. So focal length is 4
4 centimeters,
minus the
2 centimeters.
equals what?
Well, I'm going to tell you that 1/2 is bigger than a 4th. We're going to get us a negative number.
Okay, so 4 minus 2, I get negative 4.
Okay, so the location of the image is -4. Well, what does that mean? That means, well, notice that this particular thing is inside the focal length. So it's inside the focal point, and the image, pardon?
Is it at the focal point or is it inside?
No, it's inside the focal point. And so that means that if it were a positive number, it'd be over here, but since it's a negative number, it's over here. And
We're gonna get
a virtual image. So a negative distance to the image for either lenses or mirrors is a virtual image.
yeah, and that's important when we're talking about the height. Negative is inverted or upright, and we're talking about distance. Negative is going to be this side of the mirror, or it's going to be on this side of the mirror.
Now let's find the height of the image.
Okay, you got it.
And it should be bigger. It should be magnified. We should get a bigger number.
Okay, so we said the height was the
Hody-do.
Hody-do, right?
And it's negative, yeah.
Okay, and then the height of the object is 2 centimeters times a negative 4, like that, divided by the distance of the object, which
2
is
centimeters.
2. Okay, so let's see.
I'm gonna tell you that's gonna be 4 centimeters.
Divided by 2, right? Yeah, 4. Okay, so the height of the image is 4 centimeters.
And it's positive, so that means is it upright or inverted? It's
upright.
upright. And so that goes with what we would expect.
So this is a virtual image. It's upright, 4 centimeters on the same side, 4 centimeters high. Boom, okay? All right, so we've got a couple more for you guys to do, okay?
So write this information down. The focal length is 8 centimeters. The height of the object is 3, and the distance of the object is 32. Write this down.
Okay, and then I've got one more for you guys, okay, right here. So 10 centimeters, 3 centimeters, and 15 centimeters for our
So what are you going to do? You're going to do those 4 things. We could go back to that slide.
Yeah, so you're going to tell us you're going to locate the image.
Distance of the image.
The distance of the image. You're going to find the height of the image. Tell me, is it real or is it virtual? Is it upright or is it inverted?
You can do this.
You can do it. There's one more slide, Boykin. Do you want to ask this question?
For a lens with a focal length of, where would you have to put the object to get the image the same size as the object? Well, the magnification would be 1, right?
Mm-hmm.
So what we've got here is, no. All right, so the magnification is going to be 1. That means the height of the image is going to be the same as the height of the object.
Mm-hmm.
So that means the distance to the image should be the same as the distance, as the distance to the object, yeah.
It says, where would you have to put the object? So you want to know this, right?
Yeah.
So let me write out the equation.
Yeah, I haven't thought about this yet, so let's.
So we've got the magnification equals high ho equals high d ho do, right?
Okay, and so so what this means is the distance to the image is going to be the same as the distance to the object. Now let's look at the lens equation here.
Right here.
So if this is 30, what plus what is going to be 30? 1 over what plus
So
1 over
Boykin
what?
is saying if this is, we don't need this part down here, right?
No, we don't.
So I was gonna erase that part. Okay, so if this is 30, okay, what goes here and what goes here? Okay, now we just said that the distance to the object and the distance of the image have to be the same.
I'm going to say it's going to be
Is it
a
60?
60. 1/60th plus 1/60th is 2/60ths.
Okay,
Which is
260
1/30th.
which is 1/30th, yeah. Okay. All right, so the answer is, for a lens, where would you have to put the object? You have to put it at 60 centimeters.
That's twice the focal length.
Yeah. Boom. Sweet.
Sweet.
Okay, and we're done with that one. You guys have your homework. You guys go get it.